Hello. So in previous lesson we learned about the first law of motion, the law of inertia, and in this lesson we will learn about the second law of motion. So let's start the lesson. The second law of motion. What is the second law of motion? It tells us about the relationship between the force and the acceleration of an object and the mass it has. So first we'll read out the law. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. So the first question that comes to our mind, what is acceleration? When a body is moving or is at rest and due to some kind of force applied on it, if a body was at rest, goes into movement, or if a body was already in movement with a certain speed, it increases or decreases its speed, then we call it acceleration. So acceleration can be called the increase or decrease in the speed of a body due to force applied on it. So acceleration can be called the increase or decrease on the speed of a body due to force applied on it. When the speed is decreased, we call it deceleration. And when the speed increases, we call it acceleration. But generally, when we talk about it, we'll call it acceleration, and the formulas or the identities that we'll use, the mathematical deduction, we'll always call it acceleration, and for deceleration we'll take the value in negative. So the first thing, the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force. So it means that if there is an object and if we put some kind of force on it, the greater the force that will apply, the acceleration will be in that proportion. So it means that for example, there is one pencil on a table and you push it lightly, so it goes a little way on the table. So if you put a little amount of force onto it and it goes a little way. But now if you push it hard, so you're putting more force onto it, and so it goes farther away. So the mass of the body here in case of pencil remains same, but when we put more force onto it, it goes farther away. In the same way, in a playground, if someone is playing football and if they kick the ball lightly, it goes to a certain distance, but when they kick it forcibly with much more force, it goes farther away. So the mass of the body here in case of football remains the same, but when the force applied changes. When we kick it lightly, it goes farther, it does not go farther, but when we kick it forcibly, it goes farther away. So that is the relationship between acceleration and force. The greater the force applied, the greater acceleration produced. Lesser the force applied, lesser the acceleration produced. But now think about what happens when we are putting the same force in two scenarios. We are putting the same force, but the mass is changed. For example, there is in the same playground that we were before, hypothetically, we put our iron ball of same volume next to the football. Obviously, if we try to kick both of them with the same force, the football will go farther away and iron ball won't cover much distance. Why does it happen? Because iron ball has greater mass, but football does not have that mass. So in the scenario when we are putting same amount of force on two things which have different mass, the greater the body mass, lesser acceleration will be produced, and the lighter the body mass of that object, greater distance it will cover due to production of greater acceleration. So that is the first law. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force. The direction is also important. So if you kick the ball in north direction, it will go into north direction. So what does it means? That the force was applied in north direction and the ball also goes into that direction. It will never go in southern direction, in the same direction as the net force, and inversely proportional. Inversely proportional means if one is going high, the other will go opposite to it. Like if one is decreasing, the other will increase. If there is greater body mass, then there will be lesser acceleration. When same amount of force is applied, if the body mass is greater, acceleration produced will be lesser. If the body mass is lesser, the acceleration produced will be greater. One new thing that you will learn in this chapter is momentum. Momentum, as described by Sir Isaac Newton, is the product of mass and velocity of an object. Momentum is denoted by P, mass is denoted by M, and velocity is denoted by V. English alphabets. So momentum is denoted by P, mass is denoted by M, and velocity is denoted by V, as you can see on the screen. So the momentum of an object is defined as the product of its mass and its velocity. So momentum P equals to M into V, that is mv. Momentum has both direction and magnitude, hence it's a vector quantity. Momentum has both direction and magnitude, hence it is a vector quantity. The SI unit of momentum is kilogram meter per second. The SI unit of momentum is kilogram meter per second, or kgm second to the power minus 1. So if we consider a situation in which a car whose battery has died is to be pushed along a straight road to give it a speed of 1 meter per second. So we have a dead car, not a dead car, a car with a dead battery which has to be pushed on a straight road to give it a speed of about 1 meter per second, which is sufficient to start its engine. If one or two person give it a sudden push, nothing happens, because that's unbalanced force. It hardly starts. But what happens when a continuous push over some time is given to it? So what happens? But a continuous push over some time results in a gradual acceleration of the car to this speed. It means that the change of momentum of the car is not only determined by the magnitude of the force, but also by the time during which the force is exerted. So the force was given continuously over a period of time. So it may be also concluded that the force necessary to change the momentum of an object depends on the time rate. So when we are talking about that the force is necessary to change the momentum, it not only depends on the mass, not only on the velocity, but also on the time rate at which the momentum is changed. The impact of momentum depends upon its mass and its velocity. Just think about it, like there is one truck parked on a road. No one needs any kind of attention, but when the car, that truck is moving like at least of 10 meter per second or 15 meter per second or 5 meter per second speed, it needs your attention, because the impact it will produce can be lethal. In the same way, just think about a bullet which is very tiny, its volume is not that much. We have like stones like that also, but the impact it creates when it's shot and it inserts someone's body, it makes a great wound. Why does it do that? Like we throw stones at others, or we can have other things also of the same mass, and if they are thrown at someone else, it does not create that deep wound. Why does it happen? Because of the velocity at which it is exerted. So that's the thing. So the momentum, the impact of momentum depends on both its velocity as well as its mass. That is why I started by saying that momentum has both direction and magnitude, hence it is a vector quantity. Its SI unit is kilogram meter per second. Kilogram meter per second. Now we'll take the mathematical, sorry for that. So now we'll do the mathematical formulation of the second law of motion. Just think that an object of mass m is moving along a straight line. So the mass of that object is m. Its initial velocity is u. It is starting from a velocity u, and some kind of force is applied on it. Let's call it F. So F amount of force is applied on it. So when some force is applied on it, eventually it will change the speed, and the final velocity due to the force applied on it is v. So if we consider the final velocity as v, so what is the acceleration? So acceleration would be the final velocity, the difference between final and initial velocity by the time taken on it. So suppose it took t time to reach from u to v. For the velocity to reach from u to v, it took t amount of time. So the acceleration would be difference between final velocity and initial velocity, that is v minus u upon t, because the time taken was t. So the initial momentum, the momentum is denoted by t with mass and velocity. So the initial momentum would be mass, because the mass remains constant, the velocity only changes, m into u. U is initial velocity, and the final momentum would be m into v. V is the final velocity. So what becomes the change in momentum? So we talked about that the change in momentum or the change in acceleration, everything will be proportional to the force applied to it. So the change in momentum will be proportional to the final moment, the difference between the final momentum and the initial momentum, that is the change in momentum is p2 minus p1. But we have already solved that p2 equals to mv and p1 equals to mu. So the change in momentum proportional to mv minus mu. So now if we can take m common, so it becomes m into v minus u. It becomes m into v minus u. Now the rate of change in momentum, the rate of change in momentum, on screen it is written off, it will be in momentum. So the rate means by the time it took. So if the total time taken was t, then the rate would be the change in momentum by the time taken. So the change in momentum was m into v minus u, and the time taken was t. So it finally becomes n into v minus u upon t. But the change in momentum is proportional to the force applied. The change in momentum is proportional to the force applied. So we can say that F proportional to m into v minus u upon t. F proportional to m into v minus u upon t. But we have already solved that acceleration a equals to v minus u upon t. So we'll put that value here. So m into v minus u upon t. So now it becomes F proportional to m into a. F proportional to m into a. To replace this proportional sign with equals to, we have to take a proportionality constant, and the constant that we will take is k. So now after taking this proportionality constant, the equation becomes F equals to k into m into a. F equals to k into m into a. Now just think, if 1 unit force was required, 1 unit force was required on a body of 1 kg of mass to produce an acceleration which is 1 meter per second square. So if 1 unit force is applied on a body of 1 kg of mass to produce 1 meter per second square acceleration, the value of K becomes F equals to K into M into A. F equals to K into M into A. So the value of force is 1, the value of mass is 1 kg, and the acceleration is also 1 meter per second square. So everything is 1, so the value of K becomes 1. So now if we put the value of K, the equation becomes F equals to M into A, that is F equals to M. That is the mathematical derivation of the second law. F equals to M into A, or F equals to Ma. Force equals to product of mass and acceleration. So if you like to note it down, just pause this video and write it down, then restart the video again. Now the SI unit of force is Newton. The SI unit of force is Newton. It is denoted by N, as we all know. But if you have forgotten, just remember it. The SI unit of force is Newton. We write it 5 Newton force as 5 N of force applied, or 10 Newton of force applied. So Newton, in exams they will ask you to define Newton. They will ask you to define Newton or 1 Newton or SI unit of force. So Newton can be defined as an amount of unit force which, when applied on a body with 1 kg of mass, produces 1 meter per second square acceleration. So Newton is defined as an amount of unit force which, when applied on a body with 1 kg of mass, produces 1 meter per second square acceleration. So 1 Newton equals to 1 kg into 1 meter per second square. I hope you have understood the second law of motion, and if you still have any queries, please do ask me. But most importantly, stay at home, stay responsible, stay safe. Thank you.